Welcome to Roboting, a guide for total noobs. My name is Jimson Yang from 4327. I'll be covering all of the courses in here. So, throughout this course, you'll learn about the beginner's guide to robotics, and you have a basic guide for build season. So, beginning off, we have wheels. There are basic wheels, the traction wheels, the holographic drive wheels, and there are other wheels. For assembling wheels, we have hubs, bearing, shafts, and shaft collars in this picture right here. There's a shaft collar that goes through the wheel. Then it is surrounded by bearings, and then the wheel is stuck to a shaft collars, and then the hex bore hub piece together the wheel. This is basically how you have a wheel. So, just like above, this is how you want to assemble a wheel. This is the very basic idea of how wheels are assembled. If you want to read this, you can pause the video and read it now. So, wheels are used for many different things. As you see here, one example is using for a belt pulley, where they have the pulley right here, you have the hex bore in the wheel, fixed with the shaft collar in between. Again, they can use as sprockets, such as this example. This is just different examples of where wheels are used. You can see the shaft collar, hub, the bearings, the gear, and the wheel itself. For axle and bearings, so wheels need two points of support. So as you see here, for the shaft, it needs 2 points of support. That's why we have flange bearings right here, and typically one's inside and one's on the outside. Wheels, there are two different categories of wheels. There's a dead wheel, which means it does not move, and there's a live axle wheel, which means they move because there's a motor here. Now, axles and bearing blocks. So, like I mentioned above, you need two contacts of points, but some robots, they don't want to have an outside bar, just like shown above. So, what they use to still have the two different contacts is they use bearings to hold the shaft. So you have the flange bearings right here connected to it using these bearing blocks, and they hold the wheel together, and still two contact points, but it lets you for the wheels to have mobility and stuff. Again, live axle and dead axle in the wheels, so it's really which one is connected to a motor directly. So this one's going to be live. All of these are going to be live because they're connected by treads, and this one's also going to be live because there are different motors on here. This one is not powered by a motor, it's powered by this wheel spinning, so it's going to be dead. The middle ones are going to be live. Now, an important thing to note is that is no two terms, wheelbase and track width. So it's like length and width. So there are different wheels. These are called traction wheels. The above was called assembly wheels. These are called traction wheels. So these are standard traction wheels. Pros, they're one piece, they're cheap, but they're more of your standard. And I see the cons are average forfeits and they're junk when the treads are worn. Then you have industrial caster wheels. The cons is that it's industrial, so you have to have some custom machining, rework to fit it. But if they get scratched or whatever, they can still be worked. And also, they provide a lower center of gravity, so your bot doesn't tip over. These are pneumatic wheels, so one of the I would call one of the standard is that it's aggressive, big. It's you can adjust it because you can inflate it, but the issue is hard to assemble. Fall stuff can cause wobbling as here, and tires can go flat. And then you have your customizable treads. So these treads are customized. This is called a aluminum wheel right here. And these guys are expensive, but you can have customizable treads. And depending on the material or the way you have your treads, they can be beneficial in situations and unbeneficial in not other situations. So in the wheels, there's replaceable treads. There's green grippy. These are the smaller FTC wheel types. There can be used as a conveyor system. There's nitro rough top. It has great durability. And now there's pebble top. It reduces scrubbing, which we'll get back to later. But reducing scrubbing is really good. And then you have wedge top. They have really good traction. So they're typically for stuff you want to keep in place. These are the few common types, but there are other materials that are used by other teams. Now these are holonomic drive wheels. What you see here, I believe, is mechanium. First we're going to talk about Omni wheels. So these wheels can go forward, but these plastic bits, they can go side to side. So these wheels can go left, right, up, and down. It has poor traction though and vulnerable to defenses, but has complete maneuverability in all four directions. Also, there isn't as much wheel scrubbing. These are mechanium wheels, a little bit cheaper. It's vulnerable to defenses, and it's inefficient due to their low amount of friction because all of them are at an angle of 45 degrees. And like I said, they're at an angle of 45 degrees. So this is amount of force is implying. They're opposite of the direction. So you have two wheels on both sides, one on the left, one on the right. And if you have one on the left, it's going to go at the direction of the arrow. Same one on the right. And the two arrows cancel out. So you have one to the top left and one to the top right. The left and right are going to cancel out and going to drive forward. This is the same thing for backwards, and that's how mechanium wheels work, basically. This is the same thing for going left and right. So you have one wheel going like rotating backwards or forwards, another wheel doing that. One wheel is going top left and one wheel is going bottom left. So the top and bottom cancel out and goes backwards. This is another example of that. This concept can also be same for going left or right. These are other wheels. These are mostly compliant wheels. They're usually for intake. The only issue is that they lose their effectiveness when they are dirty. And then these are not commonly used, but these are ball casters. These things right here, they're omnidirectional, meaning they can move in all more than two directions instead of backwards and forwards. You can left, right, just like the Omni or mechanium wheels. These are typically for FTC robots. They're not really used. They're expensive quantities and they're needed for conveyors. They typically cannot be drive easily. So you won't often see these, but the more you know. These are continued tracks. They're superior on rough terrain and slick surfaces. They're like tank treads, good weight distribution. They're slow, heavy, complicated, expensive. Failures likely crippling, and repairs can get difficult. You won't often see these, but just in case you do, these are just continuous tracks. This is just telling you how they are used or where the wheels are. So in the back you have the drive wheel. In the middle you just have the road wheels, except for the drive wheels. This is alive. All these are dead. This is just a tension. There's no wheels here. And you can read the pro tip right there. Avoid track lengths that are nearly as long or as long as the space in between tracks, as this can lead to severe maneuverability issues. So if you want to read this, you can pause the video and just read it right now, but I'm going to skip ahead. So this is just a section covering wheels, the skills you're supposed to learn by reading it. If you want to practice or read this, again, pause the video at any time you want. So we're going to talk about drivetrains. Drivetrains are basically what they drive. So the the different drives for tank drives are 4, 6, and 8. Tank drive is meaning in the wheels can go forward and backwards, unlike the holonomic wheels. Holonomic means they can use in more than two directions, forward and backwards. For tank drive, it's like one going forward, one going reverse to make a turn. These guys, they just have to one direction they go. So major different drivetrains, holographic tank, backward forward, can more than backward forward. This can go left, right, back, and forward. So tank drives, you have 4-wheel tank drives. There's 4 wheels. It's simple to design and build, but it has a large turning radius and it has the least amount of traction. And then you have 6 wheels tank drive, so there's going to be more friction, more traction. It's durable, it's simple to build and design and program. But the issue is that there's wheel scrubbing, which again we'll mention later. And then you have 8-wheel tank drive. It's again simple to build, has more traction, better at handling ramps and other irregularities than 6 wheels, because say if there's a ramp or something and in here you can get caught here, or you can get caught like in the middle of it, then your robot's stuck. The issue is custom build, serious modification required, very likely of wheel scrubbing, and the more wheels, the more problems you can have. To scrubbing. So scrubbing is when it's kind of like drifting. It's sideways motions, but wheels aren't prepared for that, so it can damage the durability of wheels, especially like when you're spinning or turning. It also creates additional loads on the drivetrain, causing them to draw more current. This additional load can trigger brownout protection, which leads to literally your robot stop moving because there's too much power or current it's being drawn, which is really bad in a match because again, you can lose power to your robot and won't drive. So to reduce scrubbing is that you typically have a drop center, so the middle one is lower. Typically the middle one is, since it's a 6-wheel, these are going to be dead wheels, and this can be a live one. So this one is slightly centered, not slightly, it's slightly dropped, so it's going to provide more traction. It's going to have a slight rocking and some wheel scrubbing, but it's a solution to otherwise a lot more wheel scrubbing, especially if you make turns. Another way you can fix it is, first you have all even, but you have 2 Omni wheels on the back. So the Omni wheels, again, less traction, so they're able to move more. As a lower center of gravity, but again, there's less traction, so you might not have enough pushing power. Coefficient of friction, it's literally just saying how much friction there is. So for when you drive, you always want a high friction in the middle and lower friction in the back or in the front, as long as the center is high coefficient of friction. So as you see, these are smooth. There's a lower coefficient of friction, and this one's aggressive as like treads and stuff, so it's gonna be a higher coefficient of friction. This process is the same here, where in the back and the front, they're not touching the ground as much, so they're gonna have lower CF, and the one touching is gonna be higher. Same thing, Omniwheels has lower CF, and middle one has bigger CF. And CF, you want to have this so there's not as much wheel scrubbing. Hologram drive wheels, where it's basically moving all directions. Typically all directions, like forward, backwards, left, and right, without doing some weird turning or curving. Mechanism wheels, like we mentioned above, mechanism wheels turning backwards, forwards, have the angles, so the 2 angles cancel each other out, and they're able to move left and right. There's not really much pushing force. It's challenging to drive, and extra wheels and gearboxes are costly. Then you have swerve / crab. So we're going to call it swerve. These are honestly quite expensive. So this is a swerve wheel. You have one motor that's moving the wheel, and then you have another motor that's turning the wheel. It's difficult to program, and it's expensive, and you have to have an extra drivetrain. It's difficult to design and build, and it requires at least 8 motors, so 1, 2, 3, 4, 5, 6, 7, 8. 1 to turn the wheel, and 1 to move the wheel. So this most likely moves the wheel, that most likely with a tank tread or something like that, it just turns the wheel left and right. But it has mobility in, I believe, all directions. So these wheels can turn 360, and it's easy to drive. Also, it's a high speed and pushing force, and it's also agile. X-Drive Kilo. So this is basically taking the concept of Mecanium, because they're all angled at 45 degrees. So this drive forward, this drives forward. The two left and right cancel out, and they all go forward. This is basically a Mecanium in a nutshell, but you won't see this often because you just won't see this often. But it's agile. There's good program support. There's not a lot of pushing force, and it's challenging program drives that well, just like Mecanium. This is exactly what I said. So you can see the angles are exactly like Mecanium drivetrains. This is Kiwi. So 3 Omni wheels, position 120 apart, all wheels same place, remarkable insensitive to regulate in the drive surface, just compared to Mecanium or X-Drive, but there's not enough pushing force and it's difficult to code. You won't see this often, but if you do, this is just Kiwi. This is Slide. So this has, I believe, 5 Mecanium wheels, maybe, yes, and uses omnidirectional wheels. It's fairly easy to design and build. No potential for high pushing force though. Extra motors, wheels, and gearboxes required to allow robot to translate sideways. And middle wheel tends to get caught over small obstacles or uneven surfaces. So this is going left or right. These are going forward. Obviously, if you go left or right, it's going to be slower than going forward because there's less wheels. That's more or less. Then this is Octanium or Butterfly. So this one has a drop center. It's incredibly expensive. It's difficult to build and program. There's a pneumatic system. It has high speed and/or pushing force. So basically, this in a nutshell is you have a Mecanium wheels, which allows it to drive left, right, up, and down. But Mecanium wheels have low pushing force, so that's where you have basically a tank design. You have a pneumatic right here that pushes it down when it needs to have power, so it has the pushing force and power to go. And when you don't, you just want to have this Mecanium wheels driving left or right. In the picture on the left, you have the Mecanium wheels. The pneumatic isn't released yet, and on the right, you have pneumatics pushing it down, and that's where you have the power of tank. So basically, it's a tank drive and Mecanium drive all together. This is the choosing the right direction. At least in our robotics team, we're going to use tank drive always. The rest are either not effective because there's a lot of pushing powers involved, especially if you do FRC, or they're just really expensive. As you can see, like Swerve or Crab Drive, the complexity, the learning curve, it's a bunch of work, but this can decide what you want. So if there's not a lot of pushing involved, you might want to choose Omni, or if you're just really good and you know how to use the Swerve or Crab Drive, you might want to use Swerve or Crab Drive because there's more maneuverability and pushing power. So that's the skills for the drivetrain. Pause the video if you'd like to see that.